Scazza on permanently determined atoms for quantum simulations beyond the
Thank you. Good afternoon, everyone. Sorry for starting a bit late. The mic. Does it go on Zoom automatically? Probably not. Probably not. Probably doesn't matter. Does it work? Good. Sorry. Good afternoon, everyone. Sorry for starting late, so I'll try to be as on time as possible. So today I'm going to present some more or less mostly prospects for a new experiment that we are constructing in Trieste at the University of Trieste, dealing with the simulation of fermionic models and trying to extend a bit the toolbox beyond typical short-range SU2 Hubbard-like models. First of all, just to give you an idea where we are. So here is Trieste, the city. Oh, sorry, let me remove this bar. Yeah. So for those that have been maybe to ICTP, here is ICTP on the seaside, where the theorists of course are, so they can have nice bath in the lunch break. Whereas the old experimental campus is a bit up on the mountain, where there is a big synchrotron facility, and the new cold atom labs are in this building here. So conveniently next to the whole particle physics infrastructure for workshops and all type of electronic know-how and so on. Okay, so let me start now with a. Sorry, I have to go back to my screen. Okay. So just a little motivation, which is not so much needed in with this audience, but let me just be brief. So we're interested in strongly correlated fermionic systems, which of course in nature occur at almost across 20 orders of magnitude of length, energy, and let's say length scales. So from nuclei and the collisions of, for example, heavy nuclei that create very excited quark gluon matter and strongly interacting subnuclear matter, to the scale of tens of kilometers for neutron stars, where you have also similarly strongly interacting fermions very close together. So there is some general understanding that all those systems, although they have very different microscopic descriptions, can still admit some sort of universality. So trying to simulate all problems that somehow include Pauli blocking, which is clearly a common feature of all these systems, and strong interactions may shine some light on open questions in this across all these scales. And just to give you an idea of what is very theoretically challenging to treat in these systems, we're talking especially about non-equilibrium dynamics, because equilibrium physics there has been tremendous progress with computational methods. Although scaling systems computationally to big sizes with fermions is still a problem. And for the expert, this is due to the famous fermion sign problem, which is basically the fact that when you deal with fermionic wave functions, every time you swap two fermions, the wave function should get a minus sign. And implementing this constraint into computers is typically very hard memory-wise. So that's why even the most advanced numerics can still deal with exactly, let's say, with maximum 10, 20 particles system size like that. And also there are a lot of problems to treat regimes of quantum criticality. So if you look at this phase diagram here, which is sort of a prototypical phase diagram for a fermionic system with strong interactions, you will have adjacent phases with some order parameters of some kind. And there will be critical points at zero temperature, which are marking quantum phase transitions, which separate those phases. And regimes that happen at finite temperature above critical points are typically very hard to deal with because of basically the complete failure of a treatment which is otherwise very successful, which is the treatment based on quasi-particles. So in those regimes, those treatments break down, and there is a deep need of alternative approaches such as quantum simulation. And just to name a few qualitative open questions that are maybe targeted by cold atoms, still the nature of so-called non-Fermi liquids, so liquids that defy the fermionic Landau description, is still open. There are many questions on multi-orbital materials that I will tell a little bit more in the next slides. Spin liquids, quark gluon plasma, and there will be many more examples also with topological materials and so on. So in the last few years, let's say 10 years, there has been a huge progress in implementing fermionic systems with cold atoms, especially due to the advent of detection and control systems which have single atom and single particle resolution. And I divided here in this slide in sort of three main groups, starting with what are called few atom Fermi gases. So continuous fermionic systems without a lattice, which comprise, let's say, from few to 10 maximum fermions in the system, and have been pioneered by the group of Selene Joachim in Heidelberg, where you can study with single atom resolution the physics of continuous Fermi fluids. Also, the fluid is composed only by few particles, so you can also check if few particles can make a fluid or not. Then, more on the lattice side of things, there have been realizations with either, let's say, a limited number of fermions based on Tweezer arrays, which is a rather new platform. And this is an image from a Vasim Bakr group in Princeton, where you can implement sort of assembling one by one chains of fermionic atoms, and more in the scalable, let's say, around 100 particles, the famous quantum gas microscopes. These images are from a paper from Emmanuel Bloch group, MPQ, where you can have, in this case, two-dimensional Fermi-Haber model with single atom density and also spin resolution, so you can study spin correlations very efficiently in and out of equilibrium. So huge progress in the last years on the Fermi-Haber model. Now, to go beyond, so let me go back here. I wrote a line. So all these systems have been dealing typically with single band systems. So all fermions belong to the same dispersion relation. They have a identical dispersion relation. They are typically spin 1/2, and they interact with each other via short-range contact interaction between only different spins. So if you want to go beyond this, the most natural choice is to pick up some atom that offer some tools to enrich a bit the picture. And our choice for this new experiment was ytterbium, which is an atom I'm very attached to since I worked with it already during my PhD. And I think it's a very rich and versatile atom for many reasons that now I will try to tell you in brief. So the first one is that it has a very rich electronic structure typical of two electron atoms, so helium-like, which features different laser transitions from broad to narrow. And this is very useful for the whole laser cooling technology, because with each transition, you can basically find a very good regime in which it becomes useful, either to slow or cool atoms or to trap them and manipulate them coherently. And one important transition is the so-called clock transition, which is called like this because it has been discovered and used first for implementing atomic clocks. So it's a very narrow transition with a Q factor of almost 10 to the minus, the Q factor of 10 to the 17. The Q factor would be the ratio between the natural alignment of the transition and the frequency of the transition itself. This means that the two-level system created by the two states that are connected by this transition, which here I depicted with a blue ball and a yellow one, so these two, they form an almost perfect two-level system with no spontaneous decay. So this provides a very coherent two-level system within each atom, which you can use for a number of applications. As I said already, of atomic clocks. More recently in quantum computing, it has become a workhorse to create an optical qubit. But as I will tell you now, for quantum simulation, it also has huge applications in terms of the fact that you basically have two stable states with which you can create two separate orbitals using the same kind of atom. And finally, for fermionic isotopes, you have an internal spin structure for each of these two states made of nuclear spins. So these states at J equals 0, so they only have a nuclear spin left. And those nuclear spins are also very desirable in terms of their properties because they are being essentially shielded inside the nucleus. They are very insensitive to external magnetic field. So they're also very robust to perturbations, and they also make very nice qubits for quantum computing. Now, let me come to the properties that we want to use mostly for quantum simulation, so for many-body physics of fermionic systems, and that differentiate the type of things you can do with ytterbium from those that have been already done before. One first peculiar property of this atom is that the nuclear spin, being, as I said, shielded inside the nucleus, does not influence collisions. So the interactions between different atoms do not perturb the nuclear spin. And this makes it such that the system acquires an extended SU2 symmetry in the case if you have only 2 spin states, but if you now have more than 2 spin states, an SUN symmetry. So the interaction Hamiltonians that you will write will be completely manifestly symmetric in terms of the spin states of the atoms, meaning the scattering length between each pair of spins will be exactly the same independent of the spin. This has also another consequence, that if you prepare a subset of the spin states, here I'm taking this isotope, ytterbium-173, which has a total of 6 nuclear spin states. If you only prepare a subset of them, the system will remain confined in this subset because collisions cannot change the spin of the particles. And this was already exploited a few years ago when we implemented the so-called SUN Fermi-Hubbard model in a 3-dimensional lattice. And there we could study what a Mott insulator looks like for an SUN system rather than for an SU2 system. And you can see already at the level of the equation of state that things start to change. And a lot of things are still to be seen in terms of the magnetism in the system, because clearly the SU2 antiferromagnet will not find a correspondence if you have 6 spin states. The type of magnetism that will have to happen is much more complex, and there are some predictions that this could realize a spin liquid, for example. So SUN frustrate magnetism so much that it does not allow long-range order to emerge at all. So this is one first big peculiarity. A second one exploits the clock states, the fact that you have these 2 states. So you can use both of them and their spin degree of freedom as well, and look at how interactions look like between the 2 states. And now you have a new degree of freedom, this orbital label, which tells you if you are in the blue, the G, or in the yellow state, the E. Therefore, you don't have a single scattering length to describe the collisions between atoms, but you need a total of 4 scattering lengths to describe interaction in this 2-orbital manifold. And if you think about it quickly, when atoms are very close to each other, the natural basis to treat interactions comes from the molecular potentials. So those will be triplet and singlet potentials. So this means that since the eigenstates at short distance are the triplet and the singlet, and the whole pair wave function needs to be antisymmetric, also the orbital degree of freedom will need to be antisymmetric in the case of the triplet and symmetric in the case of the singlet. So you have these 2 pair states, which I call Eg plus and Eg minus, that are your eigenstates at short distance. So if you prepare your spins not in a triplet or not in a singlet, since those are the eigenstates, via collisions, those spins will oscillate and they will realize a spin exchange type of coupling. So basically, via only short-range contact interaction, these atoms realize a spin exchange coupling, which is basically the strength of which is the difference between the triplet channel interaction energy and the singlet channel interaction energy. And it turns out in ytterbium-173, this number is pretty big. So it's a very sizable energy scale that can be used to do some nice things. And last, very quickly, there is also a very peculiar type of Feshbach resonance, which we discovered back at the time together with the Fallani group in Florence in 2015, which also allows to tune the scattering between these 2 orbitals. So there is also some tunability allowed, which reminds a bit of the alkali if you want to explore tunable interacting fermions. So my main message is that using this atom, there are some nice prospects to implement models beyond SU2, so with SUN larger than 2, some multi-orbital, at least 2-orbital models. And also, as I will show you in a second, those tools are very suitable to implement quantum models based on spin impurities, on quantum spin impurities. I just added here, see also atomic mixtures in the sense that if you combine 2 atoms of different isotopes together and you can manipulate them independently, you could also address part of the things that I'm talking about, but clearly the experimental complexity goes up with respect to using a single species. And there is another main advantage here, which is the fact, and it's the last tool I'm going to bring up, is the fact that having 2 states inside an atom that can be selectively manipulated, but also coherently coupled together, is something you will never be able to do with a mixture, because you cannot, of course, transmute an atom into another by a laser. Whereas if the 2 states belong to the same atom, clearly you can do so. And the fact that these are 2 states that are very separate in energy makes it such that you can also engineer potentials with the tuned laser beams that are trapping for one of the two states and invisible for the other, or vice versa, or they can create selective mobility of the two orbitals. So you can have, for example, a lattice that makes the ground state atoms move around while the excited state atoms are very localized. And there are a number of wavelengths that are being studied right now. And for example, the group of Monica have figured out a couple new ones that are interesting to do selective state manipulations. So now let me give you an example of a type of physics problem that we want to implement using these tools, which is the famous Kondo impurity problem. And in its most simple version, this deals with a single spin impurity, which is localized inside a system of ideal fermions. So with the tools that I just told you about, you can implement this model. You just need to shine a laser potential, which can localize the excited clock state, the yellow guy, inside an ensemble of the ground state atoms that were prepared in advance. And to populate this sort of analogous of a quantum dot, you can just use a coherent laser drive to transmute a blue atom into the localized yellow atom. So if you now sort of integrate the spatial degrees of freedom out at the impurity site, you can derive those interactions that I already had introduced before. So there's an exchange interaction, which is the difference between the triplet interaction energy and the singlet one, and one that is called just the direct interaction, which is spin independent, and it's just the average between the two. And you can build a model which has as on-site interaction these ones, and includes the mobility of the blue atoms around this impurity. And so you basically come up with a model that is very, very similar to the Kondo impurity model from textbooks. It has a first term that is the kinetic energy of the blue fermions that move around. It has an on-site term, which is a spin-spin interaction at the impurity site with a strength given by the singlet-triplet energy difference. And you get an extra density term, a density-density interaction, which is not there typically, neither in Kondo materials, neither in the textbook model, which actually wants to suppress, if the interaction is repulsive, this term wants to suppress an occupation, a double occupation of the impurity site. So it sort of competes with the spin term of the Kondo effect. So it gives rise to an interesting competition, which we are now starting to study in collaboration with people at CISA and with Nelson Darko Pong at GILA. For the moment, we are just implementing exact diagonalization on a 7-site system, but we have already sort of solid proof that tuning this term, which you can do with a laser beam, essentially light shifting the impurity site, can either suppress or enhance the Kondo effect, depending on the sign, essentially, of this term. So depending if you suppress the double occupations or and incentivate them. So it's sort of gives rise to a bit of a more tunable Kondo effect that will be interesting to explore. Now, going more on the non-equilibrium side of things that maybe is more interesting for the audience here, you can imagine a multitude of situations that are interesting where you have pinned impurities inside a many-body medium, and you drive the impurities externally, either with a coherent continuous drive, or you can, something that's already been done, try to do interferometry on the impurities to sort of measure time-dependent quantities. Let's say a very famous problem that still lacks experimental realization is the so-called orthogonality catastrophe introduced by Anderson's, where you quench the interaction between localized impurities and a surrounding ideal Fermi gas. And the prediction by Anderson, also a very textbook problem, is that the state of the system at long time will become completely orthogonal to the state of the system at time equals 0. Or in the language of quasi-particles, the residue of those impurities, the quasi-particle residue of those impurities will need to go to 0 at long time. So observing this for example, in materials where there are localized impurities is hard, because if you want to observe this by a spectroscopy, what you need to detect are steep edges, so-called edge singularities in the spectral function of the impurities, which are hard to detect because you need very, let's say, high resolution in spectroscopy. And here, this cold atoms platform could offer us an alternative way, because you can look at things in time domain. Essentially, as I already said, by driving the impurities, the paradigmatic way to drive here would be Ramsey's interferometry. So you just quench the system into a superposition of an interacting state and a non-interacting state. You wait some time, and then you close the interferometer with an identical pi-half pulse, and which is some sequence which has already been implemented in a different context, in the context of Fermi tolerance. And this is a figure from a paper by the Grimm group in Innsbruck. And the prediction is that by observing the contrast of the Ramsey signal over time, you will distinguish different regions, one of which, this quantum dephasing region, should show a universal scaling related to this Anderson's orthogonality catastrophe. Okay, so I give you a last example, which may be interesting for this audience, which is the implementation of lattice gauge theories. And we have, of course, experts much more than me in the audience. I just want to advocate here that using the tools that I presented, so this state-dependent potential and this specific SUN interactions between the clock and between the two orbitals, you can basically realize lattice configurations which make the E atoms, the excited state atoms, interact SUN symmetrically with the G atoms. And in this way, you can create a quantum link model also into the non-abelian regime, which is, so proposals for creating non-abelian lattice gauge theories are quite scarce because it's really hard to sort of impose an SUN, like a non-abelian gauge constraint into a realistic architecture. And so using alkaline earth fermionic atoms, it seems that at least there's a route to realistic setups to do it. And just to give you an idea how this can work, you basically want to implement, to make energy degenerate in this very fancy lattice, all the gauge invariant states, such that they can be resonantly connected with each other. And then you try to find a configuration in which those gauge invariant states are at the perturbative level. You have to go to second order perturbation theory, in this case, connected. So in this case, in principle, you have only correlated hopping allowed in perturbation theory, and every non-gauge invariant hopping is suppressed by a gap, which protects, therefore, the gauge invariant subspace. Of course, I mean, there are still problems to face in the sense that the final gauge invariant hopping rates that you get are on the Hertz level or even below a Hertz. So this dynamics is very slow and it may be ruined by other experimental imperfections coming up. So it's definitely not the end of the story here. Okay, now in the last 5 minutes, let me just show you how we are progressing with the experiment in implementing fermionic system with single atom control. So these are some snapshots from the experiment, which is centered around a very small quartz cell to which we have already installed a high resolution objective from the top. And here you can see, for example, a picture of our magneto-optical trap of ytterbium atoms. So now I'm gonna not be much detailed in the setup itself. I'm just gonna tell you it's a very compact setup. The goal is to have high repetition rates in order that even working with few particles or few impurities, you can still accumulate a lot of data. So it is made compact and even movable in case you need to sort of replace some parts. The vacuum lifetime is already measured to be very good, around 300 seconds. And as I said, the cell is a quartz cell, is a bit of a special treatment of a cell that is now becoming a bit more widespread, which has the high convenience of being basically almost transparent to any wavelength in the visible range and even in the infrared. So you're very flexible in the choice of optical potentials that you can shine on the cloud without any problem. And also our objective is achromatic over a large range of wavelengths to be flexible in these choices. Now about the cooling sequence, it is a rather classical cooling sequence based on a commercial atom source initially. We slow atoms sort of to make them approach the center of a cell with a velocity that is low enough to be captured directly in a magneto-optical trap working on a sort of narrow line, this green line in ytterbium. In this way, you can capture atoms very efficiently. And something a bit exotic that we did is operate with only 5 beams in the magneto-optical trap, excluding the beam from the top. And this is very convenient, so we don't have to shine any cooling beam through our high resolution objective, which could somehow ruin also very sensitive single photon sensitive imaging. And this works because this line is so narrow that basically gravity that pushes the atom down can counterbalance the radiation pressure from the beam coming from the bottom. So you can operate normally without one beam along gravity. And this 5-beam mode works rather well in the sense that it can produce largish samples. with 10 to the 7 atoms at a few microkelvin or 10 microkelvin temperature. Now, going on with the sequence, for the moment, we are working with tweezers, which are micro traps made with tightly focused laser beams. So we create these traps and superimpose them to our cold sample via the high resolution objective. And then the first thing we started working on is to acquire the capabilities to image single, so one atom at a time of this new isotope, this new fermionic ytterbium isotope. So we start by making a tweezer array, which is a linear array with up to 50 traps. Then we, after the atoms are loaded in this array, we shine some resonant blue light on a strongly allowed dipole transition. And in this way, we can observe these blobs that, for the moment in this image, are multiple occupations of each trap with tens of atoms. So sort of fermionic thermal ensembles in each of the traps. Now, so the long-term goal, or more like mid-term goal, is to learn to image such number of atoms with single atom resolution. But to get started, we created single atom occupation in each tweezer and learned how to image one atom at a time of such isotope. So as I said, in the long run, we want to use each tweezer as a microtrap to create really a small, sizable fermionic system. But for the moment, we want to work first with single atoms. And now if you want to image single atoms, I think I'm running short with time, so I'm not going to tell you the details of the techniques that are available, but they basically separate in two big groups. Either you cool and you image very delicately, such that while cooling, you can still scatter some photons and get an image of the atom, or you take the completely antithetic approach. You just slam as many photons as you can, as fast as you can, and you hope that the atom stays there enough to see some of those photons. Of course, the second method I'm naming here, it works much better if the atom is heavy, because for each recoil of each photon, it will move less, it will accelerate less. And also it works well if you have a strongly allowed dipole transition such that you can scatter as many photons as possible in the shortest pulse time. And it turns out that ytterbium has both properties. It's very heavy and it has a strongly allowed blue transition. So we went ahead and tried both the traditional sort of method, which would be this so-called molasses imaging. So you collect blue photons while you cool on the green transition, and you try to be as delicate as possible. And we got very nice discrimination fidelity between having an atom or not having an atom. And you see here some images of atoms stochastically populating the tweezer traps. Or we tried also this very, let's say, fast and crude approach, just shining blue light close to the saturation intensity, as much as we had, essentially. And this turns out to also work very well. So we get a nice separation between events where the trap contains no atom and events where the trap clearly is occupied by one atom. So this already works. The only downside of this compared to the other type of imaging is that it's completely destructive. So you cannot repeat the image several times. So you can combine both types of imaging depending on need. A very good property of this second type is that will become useful to image ensembles of more than one atom, is that you are so fast that you don't have this typical downside of parity projection. So every single atom imaging that works with cooling light typically also associate atoms in pairs, and so you will only detect the parity of the atom number. So we'll only get either 0 or 1 atom, depending if the number of atoms were odd or even to start with. Whereas this fast imaging technique should instead allow to resolve them, and I already showed in the slide before such image that is a very recent result from the Marcus Greiner group, where they could indeed resolve n=1, n=2, n=3, and maybe even n=4 occupation of a lattice site with erbium atoms, so in a Bose-Hubbard type model. So now I'm just going to show our last slide, which is just preliminary results on this. So we tried already to shine our fast imaging on multiple occupations in a tweezer, and you can clearly distinguish signals from multiple occupations. So this has still to, of course, be optimized. And we also started to attempt to do imaging in free space, where you basically free the atoms from the tweezer and try to image them when they're already as far enough to give you different dots on the camera, so to distinguish them spatially. And to start with, we also use the tweezer array to do this. So we just switch off the tweezer array. In principle, the atoms will fly out of the tweezers, but we just image fast enough so that they're still close to the positions where they started from. Just to give you an idea, these images are taken with an exposure of 10, 20 microseconds, not more than that. The distance between the tweezers here is like 4 or 5 microns, something like that. Yeah, so it's still not super resolved. It's similar to Marcus Greiner's roughly resolution. And okay, just to give you the outlook, so whenever we are able to do this, our plan is to just have SUN degenerate or close to degenerate samples in such microtraps. And for example, a first experiment could be to study the release of SUN fermions from such traps and see the emergence of hydrodynamics, how it depends on the SUN character of the gas, and also something that is being also pioneered by the group of Selin Joachim to see how many particles or how few particles you need to still have an hydrodynamic medium, which is something counterintuitive because it seems like 6 or 7 particles are already enough to make a fluid that expands hydrodynamically. And another prospect we have is to investigate in such traps spin dynamics of SUN systems. So if you have vibrationally spaced levels here and you just let them interact because they overlap, these harmonic oscillator states have a density overlap, the interaction is not strong enough to scatter fermions in other states, but it can still change the spin. So you can observe spin changing processes and non-equilibrium SUN spin models. And it's a bit of a peculiar model because it has an all-to-all connectivity. So every fermion here interacts with every other fermion. So if you visualize this dimension in energy as a synthetic dimension, this is a all-to-all long-range SUN spin model, which is quite exotic. Okay, I'm finished. So let me just thank the team that worked on these results and also advertise that we have a postdoc position as I guess almost any group in the planet. And let me thank you for your attention.
Thank you very much for this nice talk. We have more questions.
Yeah, thank you. I have some questions about the shape. Because the energy scale for all this main problem, right? So you say that you want all this form.
So the study we're doing is for the antiferromagnetic. The ferromagnetic energy scale-wise is more is nicer, but it doesn't show the typical Kondo screening. So for the moment, I mean, maybe interesting to look experimentally, but there's not much theory to do about it. So in terms of energy scale, you see here, the one that dominates the whole physics is the Kondo temperature, is here. And it is, so if you don't do anything, it is around 0.1 of the tunneling. So it's scales similar, actually below even the ones that are being implemented now, achieved now in Greiner's Fermi Hubbard microscope, so 10% of the tunneling. What's nice though, are two things. One, if you use this V direct to enhance the double occupation, you can push this up quite a bit by a factor 2 or 3, which is non-negligible. And the second thing is that this is not a phase transition. So the Kondo temperature is just an indicator of some energy scale emerging, but even above the Kondo temperature, substantially above, we check correlators and you still see correlations short-ranged, a bit like when you look for AFM correlations in the Hubbard model, even if you're above the nail temperature, okay? So there can be signatures of the Kondo screening much above this temperature. So I think it's tough, but accessible. Yes, sorry, it's the same. Yeah, it's the same.
So I was wondering, you said you can do, I want to understand this, that's like a artificial system bath environment. But if you want a bath, then it's maybe not so good if you cannot put the bath items where the system is, right?
Right. No, that's exactly the point. So this extra term would suppress the bath occupation at the impurity site. Yes. So you want to tune it away from the repulsive regime. You want to either cancel it or instead try to push the bath at the impurity site by making this term negative. And this you can do artificially, yes, represented here in the scheme, by shining a laser light at the impurity site, which attracts the bath. Okay. Essentially. So you need some engineering, but it's another optical tweezer.
Further questions? If that's not the case, then let's think to see that again.